So let's go through graphing another example. So let's graph this function f at x, which is equal to 1 over x squared minus 1. Okay, so this function is slightly more complicated than the last one because this is going to have a whole bunch of asymptotes. So what do we have to do now? We have to worry about the first derivative, the second derivative to figure out when this guy is increasing and decreasing, and concave up and concave down, but we also have to worry about all of its vertical and horizontal asymptotes. And we need all of that together in order to graph it properly. So let's start. So first of all, I have it written down so I don't make a mistake, but indeed this isn't too difficult of a function to differentiate. The first derivative of this guy is negative 2x all over x squared minus 1 squared, of course. And its second derivative is given by 6x squared plus 2 all over x squared minus 1 cubed. All right, so how does this work? Let us now figure out where this function is positive and negative, and let's figure out where this function is positive and negative, and that'll give us information about where it's increasing and decreasing, and where its concavity, what its concavity looks like. Okay, so here, what are some points we care about? We're going to have a sign change at 0, so let's note this down, and we're going to have an issue in the denominator at 1 and minus 1, so let's put these here 1 and minus 1, and since between these points there are no jumps in the function, this function is going to have a consistent sign on all of these 4 intervals. And what can we see? Well, for x is less than minus 1, we have that this guy downstairs, well, this guy downstairs is always positive. And for x less than minus 1, we have that this guy minus 2x is going to be positive because it's negative of a negative number. So it's going to be positive on this, on this range. And actually for the same reason, even though we have this jump at minus 1, it's also going to be positive here. Similarly, we have that this function is for basically the exact same reasons. If when x is positive, the top is going to be negative and the bottom is going to be positive, so we're going to have that our function is, our first derivative is negative here and here. So it's going to be increasing on these intervals and decreasing on these intervals. And you might think, well, why didn't I just talk all the way about this whole interval? Why did I write minus 1 here? Well, that's because we're going to have a vertical asymptote at minus 1, as we'll see in a second. So it's better to separate this range out. Now, similarly, for the second derivative, well, let's see what happens. Well, again, we have the numerator actually never has any zeros at all, so we don't have to worry about 0, but let's be worried about 1 and minus 1. So what do we have? Well, between 1 and minus 1, this denominator is going to be negative because you'll be taking a number less than 1, squaring it, subtracting 1 from it to get a negative number, and the cube of a negative number is still negative, rather. So the second derivative is going to be negative here, and for the same reason, if you're a number greater than 1 or less than minus 1, this guy is going to be positive, and so will this guy. We're going to be positive here and here. So we're going to be concave down on this range and concave up on these ranges. So now, let's talk about asymptotes. Well, we can tell with this function that we have the limit as x goes to infinity of f at x is going to be 0. And this is also going to be the limit as x goes to minus infinity of f at x. And why is this the case? Well, in short, and this is something that we've talked about before in earlier videos, or you might have seen in your calculus class, but what's happening is you have 1 divided by quadratic polynomial, so as x goes out close to infinity or close to minus infinity, this number gets very big, and 1 over a very big number is very small. So that's why you get these two things here. We also have vertical asymptotes x is equal to -1 and x is equal to 1. So let's try to put all this information together and start graphing the function. So of course, these vertical asymptotes, why are they occurring? Because at 1 and -1, the denominator goes to 0, even though the numerator doesn't. And you might think, okay, well, we have to figure out what the limits are as x goes to 1 and -1 from the left and right. But we can actually use facts about the first derivative in order to figure that out. So let's start drawing everything out. So we have our axes, we have x, we have y, and let's indicate 1 and -1, and we know we're going to have vertical asymptotes here and here. All right, so let's talk about the range between -1 and 1. So what happens? Well, we have that on that range the function is concave down, so it's going to look something like this, and we have that it's increasing over here and decreasing down here, and this also means that we're going to have a maximum at 0. So okay, there's a maximum at 0, the function's going to be sort of a scoop shape down like this, but let's figure out what the function value at 0 is. We plug in 0 and we see that we get -1. So this function is -1 at 0. And now, well, we note that since we have a vertical asymptote here and the function's decreasing, it's going to have to go down to -infinity on this side. And since on this side the function is increasing, it's going to have to come up from -infinity on this side. So the graph is going to look like this on this region. Okay? So that's just using what we know about concavity, what we know about where the function is increasing and decreasing, which notably by the first derivative test gives us this local maximum of the function, and our information about the first derivative even told us a little bit about the limits we get near our vertical asymptotes. So now, let's talk about what happens on this side. Well, we have that past 1, the function is concave up, so it's going to have to scoop up one way or another. We have that the function is decreasing, and we have that the limit as x goes to infinity is 0. So it has to decrease down to 0, and since it's increasing and there's a vertical asymptote here, it has to come down from infinity. So the function's going to have to look something like this. Okay? And similarly, less than -1, we're again concave up, so it has to be a scoop up shape. We have that the function is increasing, and since we're increasing as we approach a vertical asymptote, the limit's going to have to go up to infinity. So the graph's going to look something like this. And you can verify this with a program with something like Desmos or Wolfram Alpha, but you'll see if you check, this is actually a pretty decent little graph of this function. And how we were able to get it is, well, exactly as I said, we cared about the first derivative and when things were increasing and decreasing, and we found a little local maximum along the way. We used concavity to make sure the lines looked reasonable. We cared about the asymptotes, and one final thing we needed is we weren't originally exactly sure where to situate this guy here between -1 and 1. So what did we do? We found a point, we plugged in 0 and saw that at 0 it was -1. That gave us a foothold, and we could draw the function from there. And this is basically how this graphing process works.